Hello learners, welcome back to my channel Shraddha's Physics. So in this part we will see the expansion of the arbitrary wave function as a linear combination of the eigen functions. Okay, and this is called as the completeness property of the eigen function. So let us write the completeness property of the eigen function, that is we will expand the wave function as a linear combination of the eigen functions. Okay, so let us consider let phi 1, phi 2 and so on up to phi n, that is the function of x, be the complete set of eigen functions, complete set of the eigen functions of some operator corresponding to a dynamical observable of some physical system then an arbitrary state or the state function, that is phi of x, this is your capital Phi. So this phi of x can be written as so here we will write the phi of x as a linear combination of the other state function, that is this capital Phi of x is equal to sum over I equal to 1 to n ai, small ai, and this is your small phi I of x whole into, this is your plus Rn of x. Okay, this is your equation 1, and here this Rn of x denotes where the Rn of x, that is equal to, this is the remainder term, after nth term. After the nth term, this is your the remainder one. Okay. So the expansion coefficient, we can write the expansion coefficients ai are chosen in such a way to ensure the smallest possible error. So now here we have to measure the error, that is to measure this error. Let us consider the following integral. Let us consider the error function, that is we can write this epsilon n will be equal to integration over mod Rn of x square into dx. Okay, so this Rn of x, we can write this Rn of x will be equal, from this equation 1 you can see this Rn of x will be equal to capital Phi of x minus of ai phi of x. Okay, so we can write from this equation 1 this Rn of x mod square dx integration will be equal to integration. So in place of Rn we can write that is your capital Phi of x minus the sum over I equal to 1 to n ai phi I of x, this is your modulo square dx, that is here we have used the equation 1, and we can write this is equal to, since this is the modulus of this equation, this is your integration capital phi of x minus sum over I equal to 1 to n ai phi I of x whole into, this is your star capital phi of x minus the sum over I equal to 1 to n ai phi I of x, this into dx. Okay, so since it is a modulus function, we can separate this two term, we can write like this, some star and into this one, that is one is the complex conjugate of other. Okay, so this is equal to, we can if I multiply we can write this is your integration phi star of x into phi of x dx minus integration phi star of x into sum over I equal to 1 to n ai phi I of x dx minus integration and the sum over I equal to 1 to n ai star into phi I, this is your phi I of x star into phi of x dx. Okay, plus integration sum over I equal to 1 to n ai star phi I star of x into the sum over again I equal to 1 to n ai phi I of x whole into dx. Okay, so now from this expression you can see for the first term we have simply multiplied all the term here, and after that you can see for the first term we can add this phi star of x into phi of x dx, that is equal to integration phi of x mod square dx minus, this is your sum over I equal to 1 to n ai, this is your ai integration phi star of x into phi I of x into dx minus the sum over I equal to 1 to n ai star, and this is your phi I star, this is your phi I star of x into phi of x into dx plus sum over I equal to 1 to n, this will be your ai star into ai. So let me write, this is your equation number 3. Okay, so now to, this is your error, this is nothing but your epsilon n. So now to minimize this error we have to take the first partial derivative with respect to ai or ai star, and it can be equated to 0. So now let us write, to minimize the error, so to minimize the error, that is epsilon n, the first partial derivative with respect to ai or ai star can be equated to 0, Okay, so now we can write, this is your, therefore dou epsilon n divided by dou ai, this is equal to, we can write, this is equal to, here you can say, if I will take the partial derivative with respect to ai, so this will be your first term, that is phi star of x, phi I of x dx, and a negative sign present here, and the next term is when you will take the partial derivative with respect to ai, then here this will be sum over ai star. So let me write the two term, so this will be equal to minus the integration of phi star of x into phi I of x dx plus ai star, and that is equal to 0. Or simply we can write this ai star, that will be equal to integration phi star of x into phi I of x into dx. This is your suppose equation number 4. And similarly we can take the derivative with respect to ai star. So now if I will take dou epsilon n with respect to dou ai star, then also you can see from the above expression. So here when you will take the partial derivative with respect to ai star, so here in this term only this part will be present with a negative sign, and also here this will be ai. So let me write the, after taking the partial derivative we will get this is equal to minus integration over phi I star of x into phi of x dx plus ai. Okay, and that is equal to 0. So here we can write ai will be equal to integration phi I star of x into phi of x dx, and that is also suppose equation number 4. Okay, so these are the similar expression, that is ai star and ai. So or let me write this is your suppose 4a, or this is your suppose 4b. Okay, now if I'll put this equation 4 in equation 3, so putting equation 4 in equation 3, putting equation 4 in equation 3, so we can write this is epsilon n will be equal to, the first term is as it is phi of x square mod square dx, minus for the second term we can write this is your I equal to 1 to n. Let me show you here in this expression, you can see here. So for the second term this is your phi I star of x into phi I of x dx. So here you can see this is nothing but your ai star, that is equation 4a. So we can substitute this value here. And similarly in the third term, this phi I star of x into capital phi of x dx, this is nothing but your ai. So if I substitute all these values, so here we can write this is your sum over ai into ai star, and again the minus sum over I equal to 1 to n ai star into ai plus sum over I equal to 1 to n ai star into ai. Okay, so this two term, sorry this is your, yes, so this two term will get cancelled, and that is equal to now integration mod phi of x square dx minus the sum over I equal to 1 to n ai into ai star. Okay, or this can be written as this is your mod ai square. I can write this is your mod ai square. Okay, since this epsilon n cannot be negative, since this error cannot be negative, so here we can write the integration over phi of x square dx, that will be greater than equal to sum over I equal to 1 to n modulus of ai square. Okay, so for any square integrable function we can write, for any square integrable function, that is phi of x, we can write limit n tends to infinite epsilon n, that is equal to 0. Or simply we can now write this is integration modulus of phi of x square dx, that is equal to sum over I equal to 1 to n modulus of, this is your I equal to 1 to infinite, we can write this is your modulus AI square. Okay. So here we can write, so the set of the function, so the set of the function, set of the function that is phi I of x is called complete, is complete. Okay. This shows that no function, this shows that no function that is capital phi of x would be orthogonal, this would be orthogonal to all the function, to all f of, sorry, this is your to all phi I of x. So let me give, this is your suppose equation number 5. So from this equation 5 we can write this limit n tends to infinite epsilon n equal to 0, and here you can see this epsilon n is nothing but integration over Rn x mod square dx. So we can write this integration also equal to 0. So now if I write from equation 5, so from equation 5 we can write, since limit n tends to infinite epsilon n equal to 0, that implies we can write this is your limit n tends to infinite integration modulus of Rn of x square dx, that is equal to 0. So the remainder vanishes. So simply you can say the remainder vanishes. Remainder means this Rn of x vanishes. So simply now we can write, therefore this phi of x now can be written as equal to sum over I equal to 1 to infinite ai into phi n of x. So that is from this expression you can see, in this expression we can simply write this phi of x equal to this much. Okay, since this remainder term vanishes, we can write this phi of x equal to the linear combination of the phi I. Therefore here we can write every physical quantity can be written as, can be represented by the Hermitian operator, by a Hermitian operator with the eigenfunction, with the eigenfunctions phi 1, phi 2 and so on up to phi n, and every physical state phi, this phi can be expressed as the linear combination, that is we can simply write this phi equal to sum over I, and here this is ai and phi I, where phi i's are, or they form, with this phi i's form a complete orthonormal set, orthonormal set, and the coefficient that is ai's are, these are given in equation 4. Okay, we have already calculated by taking the derivative, so these are given in equation 4. Hence we can write simply, therefore every physical operator, every physical operator has a complete set of, it has a complete set of orthogonal eigenfunctions. Okay. So in this way you can expand any arbitrary wave function as a linear combination of the eigenfunction, or simply we can say this is the completeness property of the eigenfunction. So this is all for today. If you have any doubt, can ask me in the comment section. Thank you all.